Next, hashing, the foundation of blockchain security. To understand chaining properly, we need to understand hashing itself. First, we'll see about hash function. A hash function takes any input at all, a text, a file, or transaction, and produces a fixed length output, often called a digital fingerprint. In our example, here the text hello blockchain goes through the SHA-256 hash function and counts out as this string 2E7B1C and so on. Every hash function worth using in blockchain has four properties. First one, deterministic. It means the same input always produces the same hash every single time. And next, it has a fixed length. The output length never changes, no matter how big or small the input is. It's one way. Practically impossible to reverse the hash back into the original input. And it is collision resistant. It's extremely unlikely for two different inputs to ever produce the same hash. The avalanche effect. There is one more property worth seeing visually because it's what makes hashing so powerful for security. It is the avalanche effect. Now, look at input A. Blockchain is secure, all lowercase, and input B. Exactly the same sentence, except the S in the secure is capitalized. One single character change. Look at the hashes. They are completely different, with no visible relationship between them at all. That's the avalanche effect. Even the tiniest change in the input creates a completely different, unpredictable hash. This is exactly what hashing can instantly reveal tampering with block data. There is no way to make a small, hard to notice edit. Any change screams for attention. Hashing plus chaining equal to tamper evidence. Let's bring hashing and chaining together and see the full picture what actually happens if someone tries to alter a block deep inside the chain. Say someone edits block 2. Its hash changes immediately, but block 3 is still holding the old previous hash value. So it is no longer matches. That link is now broken. And because block 4 depends on block 3 and so on. Every subsequent block's link is broken too. When nodes across the network compares nodes, they detect this mismatch instantly and reject the altered chain. This is the complete answer to the question what makes blockchain tamper-proof. It's not one clever trick. It's hashing and chaining working together to show the blockchain as tamper-proof. Now, let's recap the session. Let's bring it all together. First, blockchain is a distributor share ledger not owned by any single party. Transactions are validated by the network, grouped into blocks, and appended to the chain. Next, decentralization, immutability, transparency, security define blockchain's core characteristics or its value. It has evolved from a currency ledger in version 1.02, programmable smart contracts in 2.0 to enterprise platforms in 3.0 and beyond. Blocks are chained together via hashes, each one referencing the block before it, and hash functions are deterministic, fixed length, one way and collision resistant, with the avalanche effect making any tampering instantly detectable. Okay, let's close this session. That wraps up our introduction to blockchain concepts. In our next video, we will go one level deeper into mining and finalizing blocks, how that nonce we mentioned earlier actually gets used, followed by a look at currency and tokens. If this was useful, make sure to stick around for that one. Thanks for watching, and I'll see you in the next session.